All right.
Hello, hello. Welcome back for day 2 of reverse engineering. So I'm going to go through my announcements in reverse order. Today is going to be a lot shorter. So the last one was right in at about 3 hours, which I felt was somewhat necessary, but definitely excessive. So we're going to go probably about an hour today. There's only a few more basic concepts left to cover. Everything beyond that is going to be pretty self-motivated and learning on the fly type of stuff. So I'll give some general recommendations as to where to go after completing this training. Um, but yeah, so we're gonna be a lot shorter today. Hopefully, it'll be pretty digestible if you watch the last one. Couple other announcements: we're playing Seesaw this weekend for the club. So go ahead and jump in the Discord, get in voice, play Seesaw. We're going super hard on this one. Um, and we're going to try and get in the top so we can play finals. So, people in our club, go ahead and, uh, yeah, win Seesaw. If it's in super high demand, I might look at a challenge on stream, but I tend to not really want to give away solves, so we will only do that if everybody wants. Um, and then sign up for the bootcamp CTF. So we're about 2 weeks out. We have next week, 3 weeks out rather. So we have next week is crypto. Week after that is, or excuse me, reverse order. Next week is, no, that's right. Next week is crypto. The week after that is binary exploitation, neither of which you'll want to miss. And then we have one day each of hardware and penetration testing. So make sure you are signing up on play.ctf.boilers.com to register for the bootcamp. Our members, we have a little bit of extra instructions there on the site that hopefully are clear, but you can ask a question in Discord if you're not sure how to register your Purdue team to be eligible for prizes. Once again, I'll answer questions from the chat as I go, and the Docker container is here, and the source code is right here. Dungeon Smasher says, are there going to be mobile challenges? So not with respect to like iOS and Android, um, if that's what you mean. All right, so we're going to go ahead and get started. And we're actually going to do a bit of a recap of selection. So if you remember, selection is our if statements, switch cases, things that we do control flow essentially through a binary. So depending on whether checks are true or false, we will take different paths through a binary. So we're going to go ahead and hop over into our Docker container, and we're going to open up, or actually, before we do anything, we're going to pull today's stuff in the bootcamp Docker. So we're going to go into here, cd to bootcamp 2020 rev, and then I'm just going to go ahead, git pull version master. Whoop. Oh boy. Okay, I'm just going to delete it and clone it again. Okay, so if you already have the repo and you didn't make any changes to it and you're logged into Git on your Docker, then you can just do git pull. I'm going to, and if you don't have it, you can do what I'm about to do, which is git clone https://github.com/boilers/bootcamp-2020-rev into, let's just call it redo. All right, and then we'll want to go into that folder, and you'll see we have a day 2. So the first thing we're going to do actually, though, is not open up Ghidra and do something like that. We're actually going to go look at a new tool called Godbolt. It's actually called Compiler Explorer, but he called it Godbolt because this dude has an appropriately cool last name to where I think he could use it for stuff. All right, so the link was over in the slides here, but I'm going to just go ahead and type it in. Hopefully this is big enough. So we're going to go to godbolt.org/z/e65mr. All right. So you'll see over here on the left, we have our selection activity from last time. So if you were here, basically what we did is we opened this up in Ghidra and we looked at the control flow graph. And based on the control flow graph, we kind of figured out what the flag was, right? So we're just going to take a bit of a closer look at the second check today. And I'm going to go ahead and make this dark mode because that's a thing. All right, much easier on the eyes. So we're going to go ahead and take a look at check B, and we're going to get a little bit more into the minutia of how exactly these comparisons translate from C into assembly. And I'm going to do the same for iteration before we move on to a little bit more of advanced Ghidra usage with structures and a couple of other things. So we're basically just going to take a more in-depth look at some of the assembly constructs here. Okay, so if we, over in this side, scroll down to check B. Okay, so you'll notice as you move your mouse up and down on the left side here that we highlight the line in assembly that we're hovering over in our C code. So for example, this is equivalent to this in C, or rather in assembly. Okay, so we have a check, right? We pass a char star as an input. And how do we know we're passing something as an input, right? So if you remember from Monday, we talked about passing arguments in registers. So the first argument, if you remember, is always passed in RDI. And so in our function prologue, after we set up our stack frame right here in check B, we are putting RDI, right? So we're copying the value in RDI, which is this char star input, onto a space on the stack. And you'll notice that we don't decrease our stack pointer at all because we only have one local variable in this check, and so there's actually no reason to allocate any stack space. So we're not copying anything or creating new variables. All we're doing in this function is checking things. All right, I'm going to consent so that I get a little bit more screen real estate. So this first check, let's go ahead and first locate the spot where we're checking that input at 0 is greater than or equal to 0x30. So 0x30 is a 0 character. But if we go look over here, we can see first, we're getting our value off of the stack. So we just copied this input onto the stack at RVP -8. And we're going to copy it back off and place it in register RAX. Okay, so at this point here, we have input with offset 0 in RAX. Then we're going to dereference that pointer. So if you remember, the way things are stored on the system is we don't need to store everything in this array. We only need to store the 64-bit pointer to the array. And that's what we're doing. So we're storing a pointer onto the stack, and then we are grabbing that pointer back off the stack here into RAX, dereferencing it. So in EAX here, we actually have the byte at that point in the array. So then we are comparing 47 to that byte. So you'll notice here we have RAX, we have EAX, and we have AL. So that's because at different data widths, we have different mnemonics for our registers. So I'm just going to literally open a text file here because I didn't make a slide for it. But I'm just going to go ahead and make a text file and write them down. Okay, so 64-bit, we have RAX. 32-bit is the register EAX. So this is going to be the lower 32 bits of RAX. So if you imagine our register as an array of 64 bits, the 32 bits is going to be the lower half of that. Then at 16-bit, we have AH and we have AL. So that's A high which is the high 16 bits of EAX, and we have AL, which is the lower 16 bits of EAX. You won't see A high used very much. Typically, it'll just be AL, and that'll be used to store a 16-bit piece of data. And so it's sometimes a bit of an optimization to just truncate your register to a certain width instead of using RAX for the comparison, because you're basically checking less wires, and so it's slightly faster. So in any case, we now have our character at the 0 index of our input string here, and we're comparing it to 47. So if we already know what our input is, we know that our first input is 1, right? From what we talked about on Monday, we basically just went through it as fast as possible, but our first input was 1. So OX30 versus this register input, we know that the character 1 is greater than the character 0. And so if we have a 1 here, we are going to not take this jump. So let's just say we do take this jump though. So if we have something that's not in the range of characters that represent numbers, right? So 0 to 9. If we do take this jump, where does it take us? Oh, doesn't let me click. All right, L21. So it's actually going to take us down here to the next check, right? So that is exactly what we can see. If we look over here, there's no exit case if we're not within this range. We just proceed to the next check, and then we see if the next character is correct. And so actually, all you have to do to pass this check is get the last character correct, and then have every other character not be within the range that you're comparing, and you'll pass the check. So if we pay a little bit of attention to exactly how things are set up, we uncover nice little bugs like that, which I just discovered as well. All right, so let's go back to that first check. So how do we know which direction we want to be going in this? So before we look at check B, we can go ahead and look at where we call check B. So I'm just going to look at the C code for a little bit of faster identification. And then let's jump down to main in our assembly file. Where are you? Here we go, main. Okay, so before we figure out how to pass check B, we need to know which condition we want to satisfy to pass check B. So if we find the call, right, call check B. So from the calling convention, we know that the return value from check B is in RAX, which is also the same register as EAX, which is the same register as AL, like I just talked about. So we get that value in EAX, and we store it onto the stack at the base pointer -8, and then we compare it to -1. So first comparison on our result, obviously we want to see if having this comparison pass, which way we'll want to go in the control flow. So we do a comparison, which, as I talked about on Monday, is just a subtraction, and then we set our flags accordingly. And then we have jump if not equal. So if the two values from the previous compare operation are not equal, we're going to jump to L35. So L35, we're looking at grabbing this value into EDI and grabbing our stored value into EAX and then moving it from EAX to ESI, right? So that stored value, if we look back up here, is going to be the result of check B. So that's either -1 or not -1, depending. but we're assuming that it's not -1 because we're jumping if not equal to -1. So any value but -1, we're going to printf some string, which we're about to go look at, and then our second argument is going to be that value. And so if we just look over here, we can see that obviously it's going to printf error %d, but let's just go ahead for the sake of it and find that string. And a nice thing is the labels are in order, so at least there's that. Or maybe they're not. L3, L3. Here we go. Okay, so LC3 is, like we just saw over on the other side, error %d. So we're going to print error and then our -1 string. So we do not want to go to L35. We actually want to not jump here. So we want to have our value returned from check B be equal to -1. If -1 equals our returned value, then we do not take the jump because it's equal, and we're jumping if it's not equal. And in that case, we will print LC2 and then jump to L36, which just exits the program. So if we just double check up here, LC2 is logged in, which means that we were correct. And so that's what we want. We want to return -1 from our function. And so now that we've identified what we want to return from this function, we can actually work up from the bottom of it, from our return statement, in order to figure out what the best way to get that -1 to be returned is. And a lot of times this is a better way to reverse engineer than just going down through a program and figuring out what everything does, is to go from what you want and go backwards to figure out how to get it. So if we just hop back up here to check B, and then we find our return from check B. Right, so return. Now this is L23, so probably we want to find places that set EAX to -1 and then jump to L23. And I see one right here. So this puts -1 into EAX, and then it jumps to L23. So obviously we're going to want to satisfy this condition. So let's go ahead and figure out how to get through this block all the way and then jump to where we want. So first thing, we know that from earlier, our pointer to our input string is stored in the stack at the base pointer -6. So if you remember, the base pointer is always at the highest address but lowest on the stack in the current stack frame. So base pointer -8 is just the first variable, essentially, the first 8-bit variable on the stack in this program. So then here we have this add 6 to RAX, which we didn't see in our first check in the check B function. But since this is a pointer to a string, essentially what we're doing here is we're going from our pointer at the first element of the string and then adding 6 to it. So we're now pointing to the 6th element of the string, or rather 7th element, because it's 0 indexed. No, it's the 6th element. Yeah, so 0 plus 6 equals 6, obviously. So, yep. Then we grab that dereferenced byte. So we have a pointer to our byte. In fact, I can double check myself. Yeah, so it is the index 6 in our array, is what I was trying to say. So we have dereference the 6th index in our array, which corresponds to this exactly, and compare it to 47. So we already know this is character 0, and then if it's less than character 0, aka outside of the range of ASCII values that represent numbers, we're going to jump to 31, which is just going to move 10 into our return value and return. So we probably want to be greater than OX30. Next, we are going to grab our pointer again, index to the 6th element in the array, index 6 in our array, which is the 7th element. Dereference that again, and then we're going to compare that to 57, which is, as we can see over here, OX39. And then if we are not equal, or excuse me, I jumped too far. If we're greater than 57, we're going to also exit. Okay, so as long as we put in a character that represents a number, we're good to go. And then there's one more check, which is checking if we are not equal to 54. So if we're not, we're going to jump to 32, which is going to move 6 into our return value, and then jump to this return block here. All right, so hopefully that is clear enough for everybody to kind of grasp. It doesn't take too much brain power once you kind of know the syntax of the assembly instructions in order to figure out what's going on, but it does take a lot of time. I mean, that took me a few minutes to explain the equivalent of one line of code. So keep that in mind when you reverse engineering, is that every time you go down to the lowest possible level, it's going to take you significantly more time. All right, so that's a bit of a review of selection. Just remember, we compare, and then based on the value of that comparison, we jump somewhere. That's the main thing to take away. And this tool is available for anybody. If you haven't used it before, it's actually really good for learning some reverse engineering because you can type out a quick program construct and then see what the equivalent assembly is. So for example, if we have a function pointer, right? So, and then we have a function int a, and we just have this do return 10. And then in main, okay, so what we're doing with this code is we are declaring a function pointer p, right, which is void, or rather is a pointer to a function that returns int and takes no arguments. So we actually need to do p equals a here, and we're saying that this function pointer p actually points to this function a that we've defined here. And then we set this integer b equal to the return value of p, which actually points to a. So Compiler Explorer is excellent for doing stuff like this because writing a C file and compiling it and then opening up GDB would be really annoying. But instead of doing that, it has just produced the assembly right over here. And we can just go ahead and look at this and say, all right, how does this function pointer work? So we have p here, which is initialized to 0, 8 bytes of 0, right? So it's a 64-bit pointer. And this is going to be in our BSS section, if you remember from Monday when we were talking about that. And so how do we call it, right? So first thing is main, we set up some stack space. We get 16 bytes of space, easy. Then we move, okay, I'm actually going to add no pi to this because it'll be a little easier to understand. And that's the other nice thing about it, is it's easy to quickly check with different compiler options. Okay, so we are going to put the value a into p, essentially. So a is just a pointer. We know what the offset of that is, right? Although Compiler Explorer doesn't, it just knows it's a flat offset. We're moving that location into p, right? And then because of relative addressing, I guess this is not calculating it correctly, but we're going to be RIP offsetted to our BSS section, so we're going to need to index it by where RIP is. and then we're just going to move that value a into p, and then we're going to move that pointer p into RAX, and we're going to call RAX. So that's how we're going to be doing a function pointer, is we're not going to jump to A. We're actually going to call the value in a register, which, if you remember, just pushes RIP to the stack, and then it jumps to that location. So you don't have to call an address, you can call a register, which is a good thing to know if you're going to be doing reverse engineering. And then just like if we had called it normally with, so let's just compare these two types of calls. So this is functionally equivalent to this, right? So we're setting up our pointer, and then we're calling it, and then we are getting the return value from EAX into a location on the stack at RBP -4. And then we are zeroing out EAX. All right, so hopefully that is clear to everybody. Pandemic Watch says, sounds like assembler. If I sound like an assembler, we have a problem, but this is assembly, yes. Alrighty. So this wasn't in my schedule, but function pointers are a good thing to know because there's something that reverse engineer challenge writers like to abuse in order to make it way harder to figure out what they're doing. Because if this RAX got transformed a bunch, it would be a lot harder to follow exactly where it was pointing to, what function it was going to call, than it would if we just had call A, right? All right, so we're going to hop back on over. And talk about some reversing tools. So I briefly touched on this on Monday, but there's basically one big category of reversing tools you'll want to use, and then there's a bunch of other tools that can help you do more stuff. So the software reverse engineering environments like Ghidra or Radari 2 or Binary Ninja or IDA, I'm going to briefly talk through the advantages and disadvantages of each of those. And then there's some other tools that you'll want to learn, but aren't where you'll spend most of your time, right? So for these reversing environments, typically they're not GDB, right? So GDB only has a few features, and it does one thing, debugging, really well, right? But you saw when we were trying to disassemble some stuff on Monday that it's not the best at it. It basically just prints all of the text out to your terminal, and it's kind of hard to follow control flow and all of that stuff. So for anything more advanced than just a little toy binary, you'll probably want to be using one of these tools. So Ghidra, this is what I would probably recommend to almost all beginners. So it's open source, it's published by the National Security Agency, and it has basically every tool and function under the sun. The main con for Ghidra is it is extraordinarily ugly and very clunky to use. But really the amount of features that it has kind of excuses that, because they didn't spend their time on the GUI so much. They just put in the work to make a good decompiler and a good debugger and disassembler and everything like that. Another free alternative is Radari 2. So for beginners, I don't recommend that you use the command line interface for this, although there is one, and it makes you look super hacker, super elite, but it's not very intuitive. You basically have to know a bunch of sequences of characters to access the commands that you want. What I do recommend, though, if you're not a fan of Ghidra or one of the other options, is the Radari 2 Cutter GUI. So basically this adds a somewhat Ghidra / Binary Ninja / IDA-like interface to Radari 2 that you can click on stuff and use kind of like you would expect instead of having to memorize a bunch of key combinations. And I think I have that installed in the Docker, so I can maybe go ahead and show that. so I do have it installed. So the first thing you want to do when you open up Radari is AAA, which is analyze all, and then you add another A, I think, just for good measure. Disclaimer, I don't use Radari on the regular, so I might make a mistake here. And then you can do VV to get a graph of your function. You can, I'm just using HJKL, like Vim bindings, to move around this. Yeah, spoiler says too many A's in a large program will take forever, but if you don't do it, you won't be able to read it. So, up to you. I can do PDF to do something. Anyway, it's a command line tool. It's very difficult to use, at least for me. So this is why I don't recommend it for new people. But that is what Radari 2 looks like. The Cutter GUI is a lot better. It's more what you would expect from a reverse engineering environment. All right. Another option is Binary Ninja. So this one is not free. I think it's $150 for a personal license now. However, this is what I prefer to use because it is very nice looking. It's definitely the best tool for control flow analysis. It's the best tool for $75 for a student license. Good to know. It's in my opinion the easiest to use for control flow analysis and also really low level, like actually reading assembly type stuff. The con of Binary Ninja is that their decompiler is not the best. So if you're going to be decompiling a lot of large software, I would highly recommend learning Ghidra instead, just because in general it's gonna serve you better. And if you want to learn one tool, I wouldn't necessarily recommend it be Binary Ninja, just because of it's a smaller team and a smaller company, so they have a little bit less of a broad feature set. But it looks beautiful. It's really easy to use, so your mileage may vary. Then there's IDA, the classic, everybody knows about it. The problem with IDA is that, at least until recently, it was very difficult to get a legitimate license for a person. A lot of people had versions of IDA that kind of fell off the back of a truck, but not a whole lot of personal CTF players have legitimate copies of IDA. There is now a free version that can handle 64-bit binaries, so that's an option. But it can't handle alternate architectures unless you pay a pretty good amount. I think it's a couple $100 for a home edition, which gets you a license for your personal use for one architecture, and then you have to buy it again for each architecture you want to disassemble and decompile. So I don't recommend IDA to CTF players, although for industry, it's great if somebody else is footing your bill. So those are the main reverse engineering environments. If you want to use a different one and you find one that works for you, then great. For most new people, I recommend Ghidra or Radari 2 Cutter because they are both free and quite capable for everything that you'll need for a while. If you don't like the interface of either of those, probably Binary Ninja is the way to go for you. And if somebody's willing to give you $4,000 to buy something, then maybe go for IDA. Other tools, obviously we've been using a lot of GDB with the Jeff plugin. There's also the pwn_debug plugin, which is very similar to Jeff, and Jeff has significantly more features than pwn_debug or PETA each, because Jeff pretty much combines all three of them, right? So it has its own features, but then it also pulls in new features from pwn_debug and from PETA. So Jeff is what I, and probably most people at this point, would recommend. A couple of years ago, pwn_debug had some really nice features that the other two didn't, but Jeff has all of them now, so probably go with that one. Somebody asks, how does Hexray's decompiler compare to Ghidra? So I personally, and this is very much an opinion thing, and it also depends on what you're reverse engineering, I personally don't like Hexray's decompiler very much. I find it produces a lot of very difficult code to read just because of the way their decompiler works on the back end. It does a lot of random casting where it doesn't necessarily need to, and then it has fewer interface options. So Ghidra also does a lot of random casting, as you'll see probably later when we start opening it up and doing some more advanced stuff in it. But you can turn it off in the interface and it'll just show you a variable name. So I do like that about it. Yeah, so it's a personal choice kind of thing. Try them both, see what you like better. It's also pretty common to use more than one tool. For example, on any given project, I will almost certainly have Ghidra and Binja open, just because I like Ghidra's decompiler, but I like Binary Ninja for actually like determining how to exploit something, for example, because I need to be reading assembly, and I like Binary Ninja's interface for that a little better. But then if I need to find the vulnerable function, I'm going to use Ghidra, because it has a much better structure editor and propagation and type system and things like that. So try everything, see what you like, and then invest enough time in that thing that you've chosen in order to really learn how to use it. It would be my recommendation. Some other good tools to know for CTF are Anger, right? So what Anger is I'm not going to demo this or anything because A, I don't have it installed on the Docker, and B, it's a little bit outside the scope of a beginner class, but I'll mention it. So what Anger does is it is a symbolic execution engine. So normally when we execute a program on our computer, we start and it runs in one path, right? So if we hit an if statement when we're normally executing a program, we are either going to take one of the two paths. What Anger will do is it's going to take both paths, and then later you can tell it to concretize, which is a fancy word for saying, show me how you got here, the path that it's currently on. So this is really good for a wide variety of reverse engineering challenges, but it's really good for like long if statement checkers, right? You can tell Anger, hey, I want to get to the win condition of this program, and then once you're there, tell me what characters were in the input for that state. So some challenges, it's just an insta-win if you write an Anger script to solve it. Some challenges you have to put in a significant amount of effort to get an Anger script working. It all just kind of depends. But it's a good thing to know about and maybe look into if you decide you like reverse engineering and you want to invest more time in learning more about it. Then we have Z3, kind of associated with Anger. This is a constraint solver, and I'm going to talk about that a little bit more. And then obviously Compiler Explorer, really good for testing a hypothesis, right? You see you see a string of assembly instructions and you're like, hey, I think this is this, but I'm not sure. You can write the code in C that you think translates to that assembly and then test it out. And then if it is exactly what it is, then you know you've hit the money, and that's what that part of the program is doing. So it's a good tool to have. It's also really good for just learning new constructs, like that function pointer thing I just showed, or if you see some sort of derived class and you want to know what that looks like in assembly, then it's also a good thing to look at. All right, so let's look at some new stuff. So aside from selection, the other important code construct we want to know about is iteration. So this is going to be any type of loop that you have, or just repetition of anything in your program. Whoop, I don't know what I'm doing. We're going to go back to Firefox, and I'm going to look at Compiler Explorer yet again, because it's a nice way to deliver this without having to use GDB. So Z/ZZNG98 is this one. Okay, so we have four examples of loops, excuse me. We have a for loop, we have a while loop, we have a do while loop, and we have nested for loops. So we're just going to kind of painstakingly, actually, I was going to say quickly, but we're not. We're going to kind of painstakingly walk through each of these constructs in assembly, because they all look a little bit different, and it is kind of important to be able to say, okay, I think this is a while loop counting down, or I think this is a for loop going from 0 to 16, etc. And the more kind of constructs like this you see, the better you'll get at recognizing them. But we're just going to walk through these very very painstakingly. All right. So the for loop. There's just a function called for loop, and we have a prologue to this function, so we're just going to skip over that. Then the first thing you'll see that's part of the loop is we're moving 0 onto the stack at RBP minus 4. So right away, whenever I see 0 moved onto the stack, especially if it's followed by a jump, you should be thinking loop, right? Because what do we do when we do a loop? We set a counter either equal to probably a high value or equal to 0. For loops typically start at 0, unless somebody's doing some very specific stuff. And then you'll notice that in assembly, the way a for loop works is we actually jump to our comparison, which is below the body of the loop. So in C, right, we have this comparison that happens, and then the body of the loop, and then there ain't nothing down here. It just goes again. But if you actually logically think about the process of going through a for loop, first we're doing setting I equal to 0, right? And then in this function, actually, if I is not less than 20, the for loop will never run. For example, if we do I equals 21, this for loop will never run, which means that we need to check the comparison before we even execute the loop once. So if we just change that back to 0, we can continue. Okay, so we set a loop counter, right? This is our I equals 0 right here. Then we're going to jump down to a comparison function. So if you weren't already thinking that this is probably a loop based on the set the loop counter, jump down, now you definitely should be. So we're comparing that loop counter that we just set to a static value 19, right? And then if we are less than or equal to it, we're going to jump back up to here. So now that we know what our comparison is against, we know it's going to run 20 times, right? Because we're starting at 0 going until we're 19 or lower. Then right here, we have the body of our loop. And we know it's the body of our loop because after we execute this and then call puts, right? So we're just getting a string, we're just getting hello and then calling printf with that string. And just a word about puts, if you write in assembly printf and you don't have any arguments, so right now it has puts, right? But if we do hello %d and then I, it's actually going to change back to printf. And the reason is just your compiler knows that it's faster to call puts instead of printf if you're not using any format string arguments. And so you'll see puts a lot, even though people very rarely actually write puts. Then we add 1 to our what we've determined to be already our loop counter. So we add 1 to the loop counter, and then we fall back through to our comparison. And then as long as our comparison is less than or equal to, we're going to jump back up and execute the body of the loop again, add 1 to our loop counter again, until our loop counter equals 20. And then once it equals 20, we are not going to jump because we're greater than, and we are just going to return. Okay, so that is a for loop construct. They'll pretty much always take that form, except there are differences between compilers. So if we go over here, up here, and we change the compiler from GCC to Clang, what we'll see is that once again, we set up our loop counter, right? We set up the loop counter equals 0. Then instead of jumping down and then jumping back up to the loop body, Clang actually is going to perform the check at the top. So it's going to compare against OX20, and then if it's greater than or equal to that, we are going to jump down here to the cleanup of the function. Now, if it is not, we're going to go ahead and fall through, again, execute the loop body, which is printf. Then we're going to add 1 to our loop counter and store it back on the stack. So you'll notice the Clang code in this case is a little bit more complicated because I have 0 optimization. Clang is actually very respectful of the request for 0 optimization, where GCC tries to optimize even if you pass it. And then we have an unconditional jump back up to our comparison function. So semantically, these are actually the same. This for loop where we check at the top and then execute our loop body, and then unconditionally jump back up. And this other for loop, if we go back to GCC, where we set our loop body and then unconditionally jump to the bottom, check our comparison, and then jump back up to the body. They're exactly the same, and they work exactly the same, but just know that there are different configurations for the same loops. Next, we're going to go ahead and look at a while loop. So very similar thing. We set our loop counter equal to 100, and then we unconditionally jump down to our comparison function. So in GCC, this is actually going to be exactly the same as our for loop that we just did, except that instead of, whoop, this loop will never end. That should be minus minus. All right, that's better. And so now instead of adding 1 to our loop counter because of the, excuse me, instead of adding 1 to our loop counter because we have I++, we are now going to subtract from our loop counter because we have I minus minus. So we have subtract 1 from our loop counter, and then store the value back in our loop counter, and then we check to see if it's 0. If we're greater than 0, we jump back up again to the body of the loop. So let's go ahead and, just for the sake of comparison, check this again in Clang. So our while loop is up here. And once again, you'll see we set our loop counter, and then Clang, unlike GCC, is going to go ahead and do its comparison at the top, and then have an unconditional jump if the comparison is true and we've executed the loop, followed by a conditional jump back up at the top once we've looped, if we now don't satisfy our condition. All right, what about a do loop? Or is it going to look the same? And the answer is actually no. So for the do loop, we don't check first. We execute the body of the loop once beforehand. And so in this case, the GCC version looks actually just like the Clang version did for the for loop if we hadn't checked at the top. So we're executing through our loop, and then we check a condition if the condition is satisfied, and in this case it's that I is greater than 0. And the compiler actually has optimized this to check if I equals 0 by testing it against itself. Then we go ahead and jump back up to L8, which is the body of our loop. So we don't check beforehand because we have a do, and then at the end we check and then loop. And then nested for loop, very much the same thing. It's just after we do our check and then jump to the bottom, we are going to go ahead and jump back up to another initializer for a loop where we set up a second value, right? So this internal loop is at RBP minus 8, whereas the outer loop is at RBP minus 4. And I'm sorry, it's hard to see when I highlight, so I'm trying not to do it for too long. And then we go ahead and jump down, right? So jump L11 from the initializer of our inner loop, and then this is going to compare against 0. So we're just checking if we are, well, I miscoded this too. So we actually are checking to see if, oh, okay, I see what's happening. So we're grabbing our outer loop counter into EAX. Excuse me, we're grabbing our inner loop counter into EAX, and then we're comparing EAX, which is our inner loop counter, against our outer loop counter. So we are just iterating up to that outer loop counter each time we run our inner loop. And then once we no longer satisfy this condition, right, so we jump if it's less than L12. If we no longer satisfy that condition, we're going to add 1 to our outer loop, and then we're going to fall through back into our outer loop comparison. Once our outer loop comparison is false, then we're going to leave and return. So that is pretty much loops. it can be a little bit more complicated than this if you have, the loop counter going up by a power of 2 or something. But pretty much they're either going to follow the form of the for loop and while loop, or they're going to follow the form of the do loop, or they'll follow the form of that clang loop that we looked at where it unconditionally jumps to the bottom first instead of doing or rather, checks at the top and then unconditionally jumps back to the top each iteration instead of checking at the top and then jumping down to the bottom. All right. Go ahead and close that. All right, so structures is the last big topic we have to cover in order to get our basics of reverse engineering down. Basically, structures, if you don't know in C and C++, in C++ they're called classes, although you can use struct also. In C, you only have access to structs. Basically, what they do is they group data together into a user-defined object. So, just for example, if we have a struct car, we can put two things in it, int speed and char make, right? So what company made the car and how fast it goes. And then if we have int main, we can either declare a local struct of the type car, where we do struct car c, and then c.speed equals 100, c.make equals, well, it would actually be stir copy make Chevy. Chevy. Right. So this will initialize a structure, which is just a grouping of these two variables in our main function. And no, I do not want to save. So we're going to go ahead and look at what a structure looks like in assembly, because this is one of actually the harder things to do in assembly is analyze structures. It's pretty difficult, especially if either A, the binary is stripped, or B, the author of the binary intentionally doesn't give you much information about the usage of the structure entries. So let's look at an example. So there were two more compiler explorer links over here. I'm going to go ahead and open one of them up. radbolt.org/z/ this one is xwjwx9. And all right, so we have a simple structure, right? A list node, this is just a node in a linked list. So it has a pointer to the next element of the linked list, and it has a value that it's containing. So very simple. And then in main, basically all we do is we allocate, and if you remember, this is not a stack allocation, we're using malloc, so this root is actually going to be on the heap. We're allocating a new list node, and we're setting its next to null, and then we're going to add 16 list nodes, each containing a character that the user enters. So get C from standard in, put that into the nodes value, and then actually down here we should have I made this example today, so it's not perfect. Alrighty. And list add, all it does is while the root's next isn't null, aka it does point to a valid list node, it recursively will call on its next pointer, and then if it is null, it'll go ahead and add it and then return. So let's look at what this structure looks like in assembly. So let's go ahead and just look at main. So right here at our call to malloc, EAX is going to return a pointer to enough data to contain our list node, right? So you can see already the compiler has inserted the value 16 into our malloc. So that is the size of the list node structure. So we know it's 16 in size, which makes sense because we have a 8-byte integer and an 8-byte pointer. So 16 bytes makes total sense here. And then we return a pointer to that in RAX, and then we place that as a local variable into our stack, right? So the actual data of the list node is on the heap, but the pointer to it is going to be on the stack at RVP minus 16. Then we go ahead and grab that value. So we grab the pointer to RBX minus 16, or located at RBX minus 16, excuse me, back into RAX. And we're going to go ahead and move 0 into the dereference location of that pointer. So we have a pointer to our structure, we're dereferencing it and assigning that value to 0. And that's a quad word, so that's 64 bits, 8 bytes that we're assigning to 0. So why do we do that? Oh, it's because we are setting next equal to null, and next is the first entry. So essentially this this structure is not being treated as anything special in assembly, right? It's just being treated as an area of memory to assign values to. And in fact, if we go ahead and say root val equals 1,000. If we go ahead and do this, you'll see that we're actually moving 1,000 into RAX plus 8. So we very much are treating this structure as just an array, like a constant amount of data, and then the compiler is handling all of the figuring out at what point in that structure does this data go. Now, and Sandcat221, don't worry, if you didn't find it earlier, all of this stuff is available on YouTube. Our stream manager will go ahead and drop the link in there, I'm sure. But if we set value equal to 1,000 here, we can actually see that we are treating this as just a contiguous area of memory. So the compiler knows that val is located at offset 8 into the structure, and it's assigning 1,000 to that value. And so this presents actually a pretty serious problem for us as reverse engineers, because we don't have any semantic information about this structure at all, really. We know that we are assigning the first value to 0 after we initialize it. We know we're assigning the second value to 1,000. But other than this, at this point, we don't know what this is used for. We don't know it's a list node in a linked list, and we don't have any information other than it's 16 big, which actually, we'll see, is a very useful piece of information about this structure. So the best practice, in my opinion, and this may not be the same for every reverse engineer, but my best practices for identifying structures is first, locating an allocation where we are inserting at seemingly arbitrary offsets, right? So we satisfy that condition here. We allocate 16, which could just be a string, right? 16 is a common string length. But then when we're assigning, we're not like setting everything here to 0. We're setting a quad word, first of all, that's a signal, is that this is containing large elements. So we're setting a quad word to 0, and then we're setting a second quad word in this area of memory to 1,000. So I obviously would have no way of knowing what those values are, but I would probably already be thinking, okay, so we have 8 bytes of something, 8 bytes of something else. We're assigning them to different values, seemingly in different categories, and we'll talk about that in a little bit. So this is likely a structure. So if we use other context in the program, we can come more to that conclusion. So we can see, first of all, we're setting up a loop here. So we set our, like I was just talking about, we set 0, our loop counter, and we put that at RVP minus 4. And then we go ahead and jump down here, do a comparison, and then jump back up here. And we know we're going to loop this 16 times. So in assembly, once again, we're calling malloc with the argument of 16, which is good to note because likely this is the same structure that we were talking about earlier. So obviously, as you can probably guess, life gets a lot harder when there's more than one structure, especially when they're of the same size. So if we have one structure in the program that we know is 56 bytes, we can look for allocations of 56 bytes and then try and figure out which of those are that structure we're looking at. But if we have 3 separate structures that are all 56 bytes but have different sizes of data in them, it gets a lot more difficult. And I'll give a quick example of what that might look like. So if we have struct list node here, and I'm just going to go ahead and actually add. Oh man, my camera angle's not very good. I apologize. It was on top last time, and I looked like the angry kid from Maze Runner. And so I changed it this time, but it is not much better. Okay, so if we have char buff 20, let's just say, as another element of our structure. Now we'll see we get a little bit of changes in our allocation. So instead of 16, we're now allocating 32. And if we make a second structure, forgetting semicolons. But basically, I'm just going to make a structure of the same size, but that instead of a character buffer, I have integers of the same size. So instead of that character buffer, I'm just going to do int val3, and then slap a semicolon on that baby. And then if we just copy this, we know nothing about the, oh, that should compile. If I just copy that, I know nothing about the difference between these structures. So this is exactly the same code, more or less, as this is, except that we're storing our pointer in a different place on the stack. Other than that, they're functionally exactly the same, at least to an initial observation. Now, you can, in Ghidra, and I'll talk about this in a little bit, define what your structures are and then propagate them throughout your program. So this is, for pretty obvious reasons, a really nice thing. And I'm going to go ahead and open up Ghidra and show you how we do that. Okay, so I'm going to open Ghidra, and then also over here, I'm going to... Okay, so I called this redo, like a stupid person, but we can go ahead and go into data structures, and oh, that is not what I want. Okay, so I'm going to save this into a program, and then I'm going to compile it and open it up in Ghidra so that we can see how you might define a data structure. Uh-oh. Middle click. No. Okay. I need all of you. Copy. Okay. I'm not going to be able to copy it in, unfortunately. Maybe it'll just let me download the code. Does not look like it. Okay. Well, we can just go ahead and use my other example. That's fine. Okay, so we're going to use G++ here. And this is the 3 data structures directory. We're using G++ because this is C++ code and not C code. And I'm not going to show it before I go ahead and open it up in Ghidra. We're just going to treat it as if we were reverse engineering it. but the code is in the directory and in GitHub, so you're welcome to go look at it if you're not sure about anything I'm talking about. All right. Let us go ahead and, okay. So I skipped over that, but as normal, your tool chest thing should come up. If you don't have an active project, just go ahead and make a new non-shared project with whatever you want, and then click the little dragon icon to open the code browser, which is really Ghidra, but Ghidra technically has more than one tool because it has a little bit of project management stuff. Okay, so now we're going to go ahead and import file. I'm going to go back up to redo, day 2, data structures. Perfect. And I'm going to name this program 2 because Ghidra doesn't like collisions. All right. As normal, when it asks if we want to analyze it, we're going to say yes. It would be pretty hard to read without analysis. We also want to, this time, check decompiler parameter ID. We want to be sure that demangler is checked, although I'm going to show what happens if you don't. And then everything else is probably fine to leave as default. So go ahead and click OK and enter. And then if we go to main, we're going to see some stuff, right? All right, and today we're going to go ahead and open up the decompiler because it's going to make it a lot easier. So if you go to Window, Decompiler, we're going to be able to see the decompiled code. So if you haven't used a decompiler before, basically what it is a system that does its best, and it'll never be perfect, and you shouldn't expect it to be. Obviously, this is much uglier than the code that I wrote. It's a system that tries its best to reconstruct the C or C++ code from a program. All right. So we'll see right up front we have a string of length 40. We have a code location, and it's a little bit ugly, but basically we can very quickly tell, and much more quickly than if we had used just the assembly view. So we could figure out what's going on over here. We have all of our control flow markers. We know how to read assembly basically at this point. We could figure all of this out. However, we probably don't want to. And like I've been saying all along, it's much better to just take the easiest, lowest hanging fruit when you're analyzing binaries. Okay, so first thing we do is we print out, and if you've used C++ very much before, you'll recognize that an O stream is an output stream. So this is basically equivalent to printf in C++. So we're saying out, and this operator left bracket, or left angle is printing to an output stream, essentially, in this case. What ship would you like to helm today? And then it prints out again. And then we construct a basic string. So this constructor doesn't seem to do anything. But if we actually go and look at, and this is why it is important to know both assembly and how to read decompilation, we are actually getting the... Okay, so we have RDI, right? We have RAX into RDI, which is the argument to basic string. And then what's in RAX? Well, it's a pointer to RBP, and LEA loads the address of something instead of copying the value in it. So if we have a pointer to the location at base pointer minus OX40, and we LEA, we're actually getting a pointer to RBP minus OX40. And that is a minus sign, so it's RBP plus negative OX40, so it's RBP minus 40. And we're calling basic string actually with that argument. So what this does is it calls the constructor of basic string in C++. If you know what a constructor is, basically it instantiates a class on some stack memory at this address. So it is important to know assembly because over here we can't really tell that that's where that is being stored. We just see this called a basic string. So then we call standard get line, and get line, if you look at the manual, takes two arguments, the input stream that you want and the place you want to save it. And we know that this local 48 is our string, so we're reading OX40 into our string. All right. So then we do a comparison. So this operator equals equals standard char traits char and then char. So we're comparing a character against our basic string essentially. So right here we're comparing our string against the string forward unto dawn. Thank my housemate for the Halo references. And then if that comparison is false, we go ahead and check if it is Spirit of Fire. And if it is true, we print out some stuff and we create a new object, okay? So new in C++ is exactly the same essentially as if I called malloc in C. So we're getting a heap space of size OX38. So right here, we know that we have a code star star. So if we figure out what type this is, we'll figure out the type of what we're calling new on. But obviously, our program doesn't have that type information available to it, and so it's just saying code star star because it doesn't know. So we're getting 38 byte OX38 bytes of heap, and what we're doing is we're storing that in a pointer. Then we're calling a constructor on that pointer, right? So there is a calling convention, and if we look at this, we'll see called this call. So what this call does is it behaves exactly like the systemv calling convention that we were talking about earlier on Monday, except that the first argument, which is passed in RDI, is a pointer to the object, right? So when we call a constructor, the constructor needs to know where to instantiate itself. So what it does is it takes a this pointer. And when you're writing C++, you'll see this all over the place. Pun intended. And what it's going to do is it's going to offset itself by the this pointer. So if it, let's see, I think, yes. So, no, maybe better to go into this. So right here we have symbols, and so C++ is pretty nice about this. It tells us that we have this symbol Spirit of Fire, which calls this function spaceship, which is a derived constructor, right? So we have a class spaceship, and we are deriving from that class spaceship and instantiating a subclass called Spirit of Fire. And we are passing two arguments to spaceship. We're not going to worry too much about what those are, but since we see this call, we know this is a class, and Ghidra actually gives us some nice tools for dealing with classes. So if we look right here, we can see we have a class spaceship defined in Ghidra for us already because we have symbols. We can see that spaceship has three functions: crash, get class, which is a nice long function, and a constructor. And then we also know that it has some type information. Oh, if we go there. Okay, so type info. Basically, all this is going to do in most cases is just store the mangled name of the class. And we have what's called a virtual table. Okay, so vtables are important. Basically what they do is they act as if you had a structure in C with a function pointer, except it's a little bit more strictly defined. So any functions that you have in your class that are marked virtual and inherited by a subclass in C++ are going to have a virtual table entry. And when you instantiate a subclass, the vtable entries of that subclass will either point back to the function in the parent class, or they're going to be replaced with the child class's override functions. So, bit of a mouthful, but we can see in Ghidra, it's actually very easy to deal with classes and class-based stuff because it organizes it all for you, marks the functions of the classes, marks the type information, and we're pretty much off to the races. Now, let's go ahead and do a thing where we compile with the -s flag. So in CTF, this is what you're going to see most often, and also in industry reverse engineering, you're going to see this too. So we better look at it. So yes, we'd like to analyze. We want parameter ID. And all right. Okay. So now we have a bunch of things called function underscore the address the function appears at. We don't have any functions that are labeled main. We don't have anything else like that. So if we go ahead and go to entry, we can find main like we did before. We know this last argument to the libc start main function is the address of main. But even without symbols, we know a lot about this. We can see pretty much all of the standard library stuff because those will always have symbols, which is super nice. The only thing we can't see is the names of the functions we're calling. In particular, we can't see the classes in our program. So how do we define a class? So I'm going to skip over the process of finding all of the class members because I'm kind of running up on my time here. In fact, I'm already over an hour when I said I'd be under an hour. But I am going to talk about assigning a structure in Ghidra. Okay, so I'm going to close this and I'm going to go back to a C structure because it's going to be hopefully a lot easier for everybody to digest. So I'm just going to go ahead and write a program real quick. And this is just basically what's behind me in Compiler Explorer. And then, oh man, I wish I could copy and paste. All right, cool. So we're instantiating a struct, and then let's just go ahead and make sure that the compiler doesn't optimize that out. And let's go ahead and assign the value of it to -10, right? Whatever, it doesn't matter. And we'll go ahead and compile that. And we're going to strip it just for kicks. Okay, so if we go back to Ghidra, open up the code browser again. Oh, and it's off screen. Open up the code browser again and import that file. 3. And we'll go ahead and analyze this. Say yes to those options and hit OK. Then once again, go to entry. So you're seeing a pattern. Every time I start, I pretty much, if it's stripped, I go to entry. If it's not stripped, I go to main. That's pretty much just what you're going to want to do. All right. So right here we have pu var1 equals undefined malloc ox20. Okay, so based on context, let's just assume that we've gone through our program and figured out that this structure has the format, some pointer, some 8-byte pointer, some 8-byte integer, and then 20 bytes of characters, whether that's by finding a stir copy that copies into the last OX20 characters or some other such thing. What we can do is we can go down here to the data type manager. So this actually already has a bunch of data types. These are our primitives, right? We have byte, we have double word, we have void. Some of these are Ghidra provided data types that it recognizes for us. Some of them are built-in types, or excuse me, the built-in types are Ghidra's types. The generic libc types come from all of the header files on your system, right? So we have assertions, we have a lot of nice stuff, and we can browse through these all day, but we want to define our own type. So what we're going to do is we're going to collapse this, right-click Program 3, and hit New. Okay, so obviously we have a few options. We can do a type definition, we can do a structure, we can define a function. We're going to click Structure, and this is probably what you want to use most of the time. All right. So now we have this nice structure editor, and it looks fugly, obviously, but it is really nice because it works super well. Okay, so what we can do is we can add a member, right? So here we have a new data type in our structure, and we can name this structure. Let's just call it list node because we know that is what it is. And we can call this oh, excuse me. This is not the name of this structure. This is the name of our element. So if we have next, and we know it's size 8, right? Now alignment is important because what it's going to do is it's going to potentially add padding to the top or bottom of your structure depending on whether it is aligned to bytes. So for example, if you have 3 characters in a structure, most likely that struct is actually going to be 8 bytes long. It's just only going to use 3 of them. So if we okay, so I messed up actually. I'm going to go ahead and delete those. So we can go ahead and add a new, and then I actually find it easier to write up here. I was just trying to show some of the stuff down here. But we have size, we have category, description of the structure, name of the structure, etc. So I'm going to change this data type to void star, or actually, yeah, so I'm going to change it to void star to begin with. And that's going to automatically fill in the length of it for me. Now I can give it a name, so I'm going to call it next. And then I can go ahead and add a second element, which I should hopefully be able to move down using this move components up or down. And I can change this data type to int 64 because we have, through some observation, determined that it's a 64-bit int. So it is pretty helpful in Ghidra if you choose a specific size instead of just saying int. Now we can make this name val, and then we can add one more, and we can call this data type char, or rather, and then if you start typing, it'll say char star. It's actually not a char star though. We have char, and then length is going to be, if we create an array here, we can enter a number of elements. So we know this is OX20, or rather, I think I just typed decimal 20. So we can say that there's 20 characters in this. And again, that was, I found that just by right-clicking here and hitting create array. And we can call that data. All right. So now that we have that, we can go ahead and save it. And it will actually save as this name. So I'm going to change that to list node. So I was incorrect about that. My apologies. So we can tell it what to align it to, or we can just click the align and say to the nearest 8. So this is going to byte align the structure, which is the most common. And it's going to automatically detect that our size is 40 now, for what it's worth. Word align. Oh, you're right, Amar. Shoot. Yeah, all right. So Amar points out in chat that this is actually going to be aligned to the nearest 32 bytes, not to the nearest 8 on our system. No, 16 bytes is a word. What? Just kidding. All right, stop telling me stuff. We're not going to align the structure because it's actually not. All right, nobody in chat knows either. All right, so we're going to go ahead and delete these elements. You can just delete them with the right-click menu. And we're going to resave this. And now, to apply this structure that we've just defined, which if we go down to program 3, we can see appears under list node. All we have to do is right-click this and hit retype variable, and we can say list node pointer. And so now immediately, every instance of this variable will be annotated with what value or what component of the structure we're actually assigning to. So this is a list node, so we get a list node pointer, and then we are assigning to next here. And so Ghidra will pick that up after we define the type, and it'll say next equals 0. And that's basically it. That's all you got to do to define and use a structure in Ghidra. Other nice things are if you hit L, you can rename a variable. So we can say root, right? So if it's the root of this tree that we don't have because I didn't want to retype all of the code, but we'll just call it root, and then that'll propagate throughout the function you're looking at. And some other nice features of Ghidra. Obviously, we've looked at the program listing, we've looked at decompilation, we looked at the function graph. So if we graph this main function, we can see the graph of it, and if we had any control flow, we would be able to see that as well. We can look at function call trees. So if we look at malloc, for example, and we say window function call trees, we can see incoming references to malloc, which is every place malloc is called, and we can see outgoing references from malloc, which is everything that malloc calls, which in this case is nothing. But in larger programs, it's very nice to just have a concise list of everything a function calls and everything that calls it. The symbol tree we've already seen. It lists imports, exports, functions. The labels tab is a little less useful. And then obviously classes is very useful if you're doing C++. The data type manager, we kind of went over how to add new stuff as a structure. And then we can also do, let's see, some other nice things. Memory map is one of the other useful parts for quickly going to different parts of your program. So this especially matters if you're doing exploitation instead of just reverse engineering, but being able to quickly jump to your global offset table is pretty nice. You'll see it jumped us there in the program listing right here. So we have a couple addresses. We have malloc in our global offset table. And then we can also see the permissions on each of those sections. Then we have, I'm not really going to talk about scripting today. That's more of an advanced topic. We can see strings, right? So if we look at defined strings, we can just scroll through each of them. And then if you click it, it'll take you to the location it's defined at. And then once again, if we right click here and we say references, show references to address, it'll show us if there are any. In this case, there aren't, but if we find something, well, I didn't call any references to these addresses, so there won't be any, but that's a very useful item as well. And then, let's see, symbol table also can be useful, but I prefer to just use the symbol tree instead. It's a little bit cleaner. All right, so that is most of the stuff that you will need from Ghidra. All right. So I'm not going to show any obfuscation other than just a little bit of optimization today. But just know that one of the most common things that pops up in reverse engineering challenges is obfuscation. One of the easiest ways to make it hard to figure out what a program's doing is by intentionally hiding what it's doing. So this isn't secure, obviously. Anybody with enough time and willpower will be able to uncover what's actually happening. But a shocking number of companies use what's called security through obscurity, which is instead of actually securing their program, they just obfuscate it so that they hope nobody will spend the effort required to figure out what's happening and exploit it. So some of those techniques are hidden calls to functions. So I talked about function pointers, but if we use multiple in direction of function pointers, it can get very difficult to determine where a call is actually going by static analysis, and we'll need to open up a debugger, obviously, and just step into it. Another example is encrypting all of the strings in your program. I mentioned on Monday that it's much easier to reverse engineer something if you have kind of signposts. Usually I use strings as signposts. And so if all of the strings are encrypted and just decrypted right before they're printed, it becomes a lot more difficult to quickly navigate around a large new binary. Packing basically is having a small program that extracts the actual program into memory at runtime, but it will just appear as a binary blob on disk. And so statically reverse engineering that is very difficult. The main way that we deal with that is by dumping the actual binary from memory and then analyzing the memory dump instead of trying to analyze our file. Stripping, we've already seen, removes all of the symbols from a program. This just immediately makes it harder and more time consuming to figure out what's happening. It doesn't necessarily make anything impossible, but it just makes, it just adds another barrier to your understanding of the program. And then optimization. So let's just look at the program we were looking at earlier, and let's add -03. So I'm actually going to change the output back to assembly. Okay, so this is what our program looks like with no optimization. Let's go ahead and add -03, which is highest optimization. So the program immediately just shrinks, and that's because the compiler did a little bit more work to figure out some more efficient ways that it can do things. Now, that's a little bit of a problem for us because it becomes a little bit less easy to quickly identify arguments to functions. It becomes a little bit more difficult to, especially in like this function, figure out what's happening. So this is the whole list add function, and so that is yeah, that's not great because this is a recursive function that does some checks and then calls itself if the check isn't satisfied, but instead it's just converting it into a loop, right? So functionally it's the same, but it appears a lot different when you're reverse engineering it, and it makes it more difficult to figure out what's happening. All right, so some demos of real challenges. I'm going to leave this for maybe a YouTube video later so that we don't go too far over time. But I'll do at some point a couple demos of real challenges. If you're in Boilers, obviously just come to the Seesaw channel and play Seesaw because those will be real challenges. And then some RE tools and techniques. So the only one I'm really going to go in depth in is GDB scripting because it's actually very simple, but it's very nice. So if we go to our bootcamp rev folder and we go to day 1, and we go to that RE challenge demo, I'm going to talk through how to write this solver script. So the first thing you want to do for any GDB script is import GDB. So this tells GDB when you source it that you're going to import the GDB library that allows us to interface with it. So the GDB library in Python is very simple. There's only a couple things that you really need to know in order to be able to write a script, and the rest of it is just Python logic. So the first one is gdb.execute. Literally what this does is it takes your command, and this is just a straight up GDB command as if you were running it on the GDB command line, and then it takes two arguments from t2y and toString equals true. So this, and I might have those in the wrong order, but those are the two arguments. Basically, if you don't set both of those to true, you can't get output from the command. But if you set them to true, and you say s equals gdb.execute your command, we're going to actually get the output of this command, just say it's info file in a variable. And then we can, print s.splitlines or something, just to show that this works. So let's just go ahead and gdb-q program. And let's go ahead and source solve.py. So you can see we just printed out the line split up version of running the command info function. And for most purposes, that's enough. You only need to know that you have gdb.execute, but I'll go ahead and explain this. So right here, I'm subclassing the breakpoint class, and the documentation for all of this is online. If you just search GDB Python documentation, you'll find it. And I'm overriding the stop function in the breakpoint to return false. So basically, breakpoints, you can control whether the program actually halts when it gets to them, or whether it just says, all right, I got to the breakpoint, and then keeps running. So in this case, we want it to keep running because we want to continue to be able to check without having to run continue every time. And the breakpoints, once again defined in the documentation, have a couple of parameters, or a couple of locals to them. We can set the ignore count to a really high number. This is the number of times that we can hit that breakpoint without actually stopping on it. And then we also have the hit count, which is the number of times that we've actually gotten to that breakpoint. So right now, what we're doing is each time we guess, we're setting the hit count to 0, and then we're just writing our guess to a file, and then we're running our program with the input from the file and the output to null. Pretty simple. And obviously we don't have true on these calls because we don't need to get the output, but if we did this, we'd be able to say result equals that. And then what we're doing here is the breakpoint hit count is going to increment every time we hit that breakpoint. And so what we can do is we can test if our breakpoint hit count is higher than the length of our flag, or the length of our current test. And if it is, that means we have gotten to the correct point more time, or the same number of times as we have input characters, which means all of them are right, which means we can go on and add another input character to guess while keeping all of the ones before the same. And then that's pretty much it. We're just iterating through all of these guesses. We have a known address that we want to brute force, and we're just using a couple of GDB commands in a loop with Python in order to get there. And then I already talked about anger and Z3 and kind of what those are, so I'm not going to go back over it again. Maybe a video for another time. So yeah, theoretically, you should have at least, or probably more than enough knowledge to solve that initial challenge that I handed out. If you want to go try your hand on it, it's obviously in our GitHub repo. But yeah, let's go play Seesaw.
So
Nathan, do you see any questions from Discord or anything?
There's a yeet from Amar.
Oh, good. Indeed, yeet. Yeah, I didn't see a whole lot of questions. I wasn't expecting too many people today since I A, covered most of it on Monday, and B, uh there's a bunch of other stuff. No problem, Pandemic Watch. This was not my
Yeah,
best work. Full disclosure, I started prepping for this about 45 minutes before I started the stream. So if you wanna see an actual good instruction, go watch the one from Monday at our YouTube channel.
they were both good. Monday was amazing though, like really amazing. So watch that if you haven't.
That is a Vive base station, but it is not mine. It's my roommate's. Imminent Seesaw is going well. I think we found well, their infrastructure is not going well, but we found some nice bugs.
They
Alrighty,
fixed that
everybody.
one now, so that's good. But sweet. See you guys. Play Seesaw.
Crypto is on Monday, so look forward to that. Brandon will be teaching. And it'll be drastically different from what we've been doing this week. So if you were looking for a shift in atmosphere, that is what you should try.